Ladies and gentlemen, welcome to lecture number 2 in the course EEE 4682. This is a course in communication systems. We'll be looking at data transmission impairments. The presentation outline will look as follows. We'll look at the introduction to the topic. We'll talk about the elements of a digital data communication system. I'll talk about signal attenuation, noise and noise categories, all the way up to channel capacity. And at the end, I'll give some tutorial. Now, so we'll briefly discuss the digital data communication system, look at attenuation, look at noise in both analog and digital communication systems before we delve into tutorials. Now, a digital data system will comprise of the source, analog digital converter, encoder, the modulator unit on the transmission part, and then on the receiving part, it will have the modulator, detector, decoder, digital to analog converter before the information is relayed to the user. Brief discussion about each of these elements will be as follows. The analog digital converter, as we know, converts analog signals into digital. And then once this information is in digital format, then you apply the encoder, which is basically the process of putting a sequence of characters, numbers, letters, and so on into a specialized format for the purpose of ensuring efficient transmission as well as maximizing storage space. And the decoder will basically remove these sequences of characters, numbers, and punctuation. It is basically the opposite of an encoder process. It's a process of conversion of an encoded format back into the original sequence of characters. Then next we've got the modulator, which basically adds a carrier to the message for the purpose of long distance transmission, and also for the purpose of minimizing noise, and also reducing the antenna, the size of the antenna. And the demodulator unit will basically remove the carrier at the receiving end. The carrier, which is usually high frequency signal, this will be removed from the message. Then the message will be relayed to the end user in its original format. Next, I want us to talk about signal attenuation. As the signal travels between the transmitter and the receiver over some given channel, this signal is bound to lose some energy or become weaker, largely due to distance. So basically, its energy will lose its energy. And when a signal travels through a medium, it loses energy, overcoming the resistance of medium. And usually to remedy attenuation, repeaters and amplifiers are usually used along the way. These are intended to compensate for this loss of energy by way of regenerating the signal or by way of amplifying the signal. And the formula to calculate attenuation dB is 10 log P2 over P1, where P1 is the input signal, P2 is the output signal. So basically, you can, given the input power from the transmitter and the output power at the receiving end, you can calculate attenuation using this formula, which gives the value in decibels. The signal here, the diagram here illustrates if at point 1, this is the original signal which you are transmitting over some transmission medium, and that at point 2, which is some distance kilometers away, and this is at the receiving end. So if I know the power at point 1, I know the power at point 2, I can calculate attenuation by using the formula which we just looked here. So basically, once the signal, you notice that in this setup, the original signal has got higher strength compared to the attenuated signal here, which loses strength. And in order to regenerate and increase, we can actually pass the signal via some amplifier or a repeater. And then at point 3 here, you get the signal as good as it was at the original. So basically, that's how the process of attenuation looks like. The idea really is to ensure that okay. Next, I want us to talk about signal attenuation in terms of the factors that. Now, signal attenuation depends on the following factors: distance between the transmitter and the receiver. The longer the distance between the transmitter and the receiver, the higher will be the value of the attenuation. And also the type of media, as we know, different types of media. You have media using cables, media using the radio interface. Each of these different types of media will offer different values of attenuation. Also frequency, at higher frequency, we expect attenuation to be low, but as the frequency reduces, we expect that attenuation will be high. Now, received signal strength must be enough to be detected at the receiver, and it must be sufficiently higher than the noise, to be received without error. Otherwise, should noise and other impairments be greater than the signal, then you get the signal being attenuated, basically buried in the noise. Let's talk about noise. Noise is defined as an unwanted signal that falls within the wanted signal. And there are various classes of noise. We've got noise can be classified in terms of external as well as internal. And so basically noise whose source are external to the receiver, and you've got noise whose source are within the receiver. And those that are within the receiver are basically classified as internal noise. So let's look at each of these classifications in a bit of some detail. External noise, noise created outside the receiver, and examples of such, we have what is known as atmospheric noise, extraterrestrial noise, and industrial noise. And talking about atmospheric noise, this is noise caused by lightning discharge in a thunderstorm and other natural electrical disturbances. This type of noise do affect a wider spectrum due to its random nature. This noise actually becomes even more when operated in the VHF frequency range or above, but anything below the VHF, 30 megahertz and below, normally you don't, you get this type of noise. Next, you've got extraterrestrial noise. This is noise emanating from the sun as well as from the stars, and the one that comes from the sun, it's called solar noise. It can have a temperature exceeding 6,000 degrees, and such a temperature, it radiates energy with some noise. So, but under noise coming from the stars is called cosmic. So cosmic is noise from the stars. So those are the two categories of extraterrestrial noise, cosmic as well as solar noise. Next, we've got industrial noise, which is another example for external noise. This is noise from cars, aircrafts, industrial machines. It can range from 1 to 600 megahertz, and this noise can affect the transmitted baseband signal. So Moving on from external noise, let's talk about internal noise. And under internal noise, this is basically noise generated inside the transmitters, receivers, and communication cables. It's a function of so many factors such as resistance, width, and temperature. But far more disturbing of the various types of internal noise is thermal noise, and we'll discuss about it in a little while. Now, examples of internal noise, there are quite many there. We've got crosstalk. Crosstalk is unwanted coupling between signal parts. Usually it occurs by electrocoupling between nearby twisted pairs, and is something usually we experience by anyone who, while using a telephone, you are able basically to hear what the other person is saying. Somebody else joining your conversation. Impulse noise, usually non-continuous noise consisting of irregular pulses. They usually show itself by way of noise spikes of short duration, but of relatively high amplitude. It is usually generated from a variety of causes. Some of it are external electromagnetic disturbances, such as lightning, as well as faults and flaws in communication system. Now, impulse noise is generally only a minor annoyance for analog signal, and its effect may not really be so bad for analog signal, but however, if you talk of digital signals, impulse noise is the primary source of error in digital data, because that impulse can change a 1 into a 0 and a 0 into a 1. That's why impulse noise is quite a primary source of error in digital communication. Next, we've got intermodulation noise. Now, noise, this is noise due to signals of different frequencies sharing the same transmission medium. And the way this type of noise is, basically generated would be such that it is produced when the signals at a frequency that is the sum or difference of the two original. So it's basically derived The effect of intermodulation noise is to produce signals at a frequency that is the sum or difference of the two original signals. So you have two signals sharing the same transmission line, and as the signals travel through this medium, it can happen that the two signals of different frequencies can add up together, or they can subtract from each other. So usual intermodulation noise will have, the effect of intermodulation noise is basically to produce a signal at a frequency that is the sum or difference of the two signals. This derived signal could interfere with the intended signal, and is also, efforts must be made to minimize it. The other type of internal noise is thermal noise. This is noise due to thermal agitation of electrons. This type of noise is present in almost all electronic devices and transmission medium. It is a function of temperature, among other things. It is also a function of resistance, temperature, as well as bandwidth. So thermal noise power can be calculated as KTB, where K is Boltzmann's constant, T is temperature in Kelvin, and B is bandwidth. And the Pn there is basically the noise power. So yeah, that is noise power. So you have what Pn equals noise power. This one should actually be also Pn, basically to signify noise power. Then thermal noise power is therefore a function that can be calculated from Pn equals Vn squared over R. When you substitute for making Vn the subject of the formula, you have Vn squared equals Pn over R, which gives you Pn times R under square root. And substituting the values for Pn, we get 4k TPR, and that is our equation 2 for calculating thermal noise voltage. Next, let's talk about short noise. Short noise is another example of eternal noise. This is noise due to random fluctuations in electron emission from cathodes in vacuum tubes. It also occurs in semiconductors due to the liberation of charge carriers. So as the charge carriers move and get liberated, you have some noise being generated, and that noise is short noise. It can be calculated as short noise IN equals square root of 2 IDC plus IBQ, where IDC is the DC PN junction current, the B there is the effective noise bandwidth, while the Q is the electron charge equal to 1.6 times 10 to the power minus 19, and IO is the reverse saturation current. Next, let's talk about signal noise ratio. This is defined as the ratio of the signal power to the noise power. It can also be expressed in decibel as 10 log PS, where PS is the signal power, divided by PN, where PN is the noise power. Noise figure is basically signal noise ratio at the input. Okay. This is the ratio of the signal noise ratio at the input to signal noise ratio at the output. It is denoted by the letter capital F, and the capital F is equal to signal noise ratio at the input divided by signal noise ratio at the output. Noise factor is nothing but noise figure expressed in decibels. So whatever the value of F, when you express it in decibel by multiplying 10 by 10 log F, you get your noise factor NF. Let's talk about channel capacity. Most important question for communication channel is the maximum rate at which it can transfer information. There is a theoretical maximum rate at which the information passes error-free over the channel called the channel capacity C. Now, channel capacity of a noise-free channel is given by C equals 2B log 2M, where B is the bandwidth, M is the voltage level, number of discrete signals, and C is the channel capacity. For a noise channel, the noise channel condition data rate can be expressed as C equals B log 2, 1 plus signal noise ratio, as shown in equation 5 here, and where signal noise ratio is nothing but 10 log to the base of 10 PS over PN. Therefore, there are two factors that determine the channel capacity, and these are bandwidth as well as noise. These are some of the tutorials which I would want you to try. This marks the end of our lecture. Thank you for listening.